This is related to the module 1 of facts concept. Myself, Dr. VVS Acharya, professor and working in Department of EEE in Lendi Institute of Engineering and Technology. And first of all, in the module 1, we will discuss about the basic things in related to the facts, that is why we need transmission interconnection, what are the disadvantages of HVAC and HVDC system. Then we go for the what are the basic types of fact controllers. In this module 1, first, what is the need of transmission interconnections? Uh, Generally, to minimize the cost, the facts actually small distribution generation, because more economically viable if there is a backbone of a transmission grid. Like that, if the transmission interconnections is there, number of generation requirements also reduces, automatically the cost of generation is reduces, and continuous power supply point of view also always require interconnections. And another major thing is power transfer from the surplus area to deficient area, that is also due to the interconnections. These are some of the advantages and key factors using transmission interconnections. And coming to the disadvantages of HVDC transmission, actually the generated power always in AC, and distribution of the particular power or requirement of the loads mostly depends on AC. Only transmission purpose we are converting AC supply into DC, then at finally it is converted as DC to AC. That means you need some converting stations at generation end as well as the distribution end. This is somewhat costly, and the switchgear equipment also required, DC switches and circuit breakers. There are some limitations and comparatively it is costly. So these are some disadvantages due to the HVDC transmission. And coming to the disadvantages of HVAC transmission. So always AC means their existence of inductance and capacitance. Automatically problems are encountered into the system, like skin effect, and more copper is required and losses also increased. The construction of AC transmission lines more complicated as well as costly. So this is the disadvantages, and the most final disadvantages, it is not flexible. That means we are not controlling the power in AC. That is a major disadvantages in the HVAC system. That's why this point is always an inspiration to for the fact controllers. So general two area system, you once you check that this is a power flow in parallel paths. AC system power flow we are designed in the parallel paths as well as radial line, that is called as radial lines. You see this is indicating surplus generating area. This is local load. Okay, another side is this is surplus. This is also generating station 2. This is local load related to the generating station 2. Okay, always power can transfer from surplus generation area to deficient area, that means left side to right side. Okay, but always this power, you clearly observe that always this power can be transferred based on the impedance only. So we are not controlling the AC power. You clearly observe that impedance of the first line is less compared to the second line, so maximum power can be transferred from this top line. That means 2 by 3 power can be transferred from the top line, and remaining power can be transferred by the 1 by 3. So we are not controlling based on the impedance, power can be transferred from uh, the surplus area into deficient area to satisfy the local needs of the load. So, that means this conductor, based on the impedance, it is always overloaded. The load on the second conductor is less. So this is the disadvantages in the AC transmission. Once comes into the second line, second picture, you clearly observe that we are incorporating some converting stations. We are creating it is as a HVDC line. So once you are converting or incorporating the converting stations means automatically the power can be transferred from the second line always controllable. That means you are controlling the power in the second line. Okay, uh, but uh, coming to this line, automatically it is controlled. Once you control the power from this line means automatically this will be controlled. So but the major disadvantage is this is costly. Then it is comes into the picture. You see that this is a we are placing variable impedance type fact controllers or variable phase angle type fact controllers. So the fact controllers is simply say that this is not a fixed value, it's a variable impedance type. Maybe the impedance may be the capacitive nature or inductive nature. We are placing at any line, automatically you are controlling the power in this particular line. So once you are controlling the power in this particular line, automatically second line also controlled. So same thing will be happened by using variable impedance type fact controllers or variable phase angle type fact controllers. So these are the advantage of fact controllers once incorporating in the transmission line. Once you are incorporating in the transmission line, automatically power in this line controlled. Once the power in this particular line controlled means automatically remaining power can be transferred in the above line. So this is somewhat advantage compared to the HVDC system. No need of converter station, automatically cost is minimized. This is suitable and comfortably the reactive power compensation is high here because this is always not fixed value, this is variable value. So automatically this is having good results. Same concept can be explained in a mesh network also. Previously it is a from source end to load end, like the point 1 to point 2. Here this is a meshed system. Meshed system means there is a closed loop system like that. In that also clearly you can see the diagram A or B or C, D. So once our objective is increase the power transfer capability of the AC system, automatically we are incorporating one capacitive variable capacitive nature fact device in this particular area. Automatically overall impedance will be reduces, overall reactance will be reduces, power transfer capabilities increases. This is one method. Otherwise, reversely you can incorporate variable inductive nature factors in the BC device. Automatically what happened, BC transmission line, automatically the power flow in the BC transmission line is reduced, from AC is increased. Like that also possible. Instead of this, you can use phase angle, variable phase angle type fact device. Like that we are using, automatically the power transfer capability is controlled in the AC transmission systems. That's why these devices is called as, after incorporating these devices, transmission systems is called as flexible. That's why it is called as fact devices, flexible AC transmission systems. So from that we are going to the, after that we are going to some limits. What limits the loading capability? So the loading capability limits can be divided into three types. That is thermal limits, and the second one is dielectric limits, and third one is stability. So due to these three causes, due to these three constraints, automatically which affects the loading of the transmission systems. First we go for the thermal constraint. Thermal constraints always related to the um, ambient temperature and wind conditions of the conductor and ground clearance, as well as the aging effect of the uh, particular conductor. So that's why we are always prefer that once you consider this consideration, we can always say that we can take the readings worst ambient environment case scenario. Like that some utilities assign the winter and summer ratings also. Like that, we can consider this thermal constraints. Then you go for the dielectric. Dielectric means insulation point of view, many lines are designed very conservative. That means if, for example, a rating you can expect it is a 500 kV, the insulation you provided up to 550 kV. That means 10%. If you increase the voltage also, the system will be withstand. More than that, it may insulation get failure. That's why care is then needed to ensure that the dynamic and transient power voltages are within the limits. Present actually modern graphless arresters or line insulators with the internal graphless arresters are powerful thyristor controlled over voltage suppressors at the substation can enable significant increase in the line and substation voltage capability. So coming to the third one is third constraint is stability. So there are number of stability issues that limits the transmission capability. These are already we know in the power systems. That is nothing but steady state stability, dynamic stability, and transient stability. This is also comes into the picture is frequency collapse and voltage collapse and subsynchronous resonance. These are the stability issues also matters why limit the transmission capability. That means, for example, frequency collapse, whenever the active power generated and active power utilization, both are not matched, automatically frequency will be oscillated. A reactive power generation and reactive power absorption, it is not matched, automatically voltage will be disturbed. Like that, if any sudden changes in the voltages, it is not comes into in time, automatically stability issues will become. These are all comes into the picture while considering the transmission capability of any line. So these are the limitations of transmission capability, that is thermal and dielectric and stability. And coming to the dynamic stability consideration of a transmission interconnection, you clearly see that we are considering a simple two machine system. In that, this is indicating surplus generation. Second one is indicating the deficient power generation. So the transmission line, you clearly observe that represented as a inductance. That means this is purely inductive. We can neglect the effect of resistance and capacitance of the particular transmission line. So we are controlling both the active power and reactive power. So these are the considered to be two stiff buses. The bus voltage here at station 1 is E1 at an angle of delta 1. Here the bus voltage is E2 at an angle of delta 2. Delta 1, delta 2 is load angles. Otherwise it is called as phase angle also. The difference between these two is nothing but delta. Delta 1 minus delta 2 is equal to delta. This is the phase difference between the E1 and E2. So the difference between these voltages is represented as EL. This is called as driving voltage. The driving voltage always perpendicular to this flow of current. Current flow is always perpendicular to this driving voltage, because we are considering the transmission network is purely inductive. That's why always current lags by driving voltage by 90 degrees. So these are the some phasor representation. Once you go into the deep analysis with the cosine and sine angle representations, you can clearly see that always E1 cos alpha or E1 cos delta is lies on E2 and E2 cos delta are lies on E1. So E1 cos delta and E2 sine delta differentiated by 90 degrees. That's why you are represented here. This is E1 sine delta. Both are parallel. That's why here also you represented as E1 sine delta. And you can observe that this is E2 cos delta. That means with a 90 degrees difference with E2 sine delta. Once you represent E1 cos delta, E2 cos delta, then you can go for with 90 degrees by E2 cos delta, E1 sin delta and E2 sin delta. So once you are representing this, we can go for the currents, that is active components of current and reactive components of current. The active component of current of phase 1, that is nothing but always lies in the bus E1, that is IP1 represented in the bus E1 and IP2 is represented in bus E2. So reactive current always 90 degrees phase opposition, phase difference. That is IP1 is here, that's why 90 degrees difference IQ1. So this is IP2, 90 degrees difference with IQ2. So this difference is nothing but E1 minus E2 cos delta. This difference is nothing but E2 minus E1 cos delta. Then you go for the final active and reactive power flow phasor diagram. So what I discussed previously, we are represented in clearly here. So from here, we can calculate the power. So that's why power in terms of the load angle is nothing but E1 E2, E1 E2 by X into sine delta. The active power representation is E1 E2, E1 E2 sine delta by X. So you can clearly see that power angle versus, okay. So these are the, okay. So you see this is power angle versus power characteristics. This is P equal to E1 E2 by X sine delta. Once delta value is 0, automatically active power is 0. If the delta value is 90 degrees, the active power is increased to maximum value. So the delta value is 180 degrees once the active power comes into the 0. So if you change the impedance value, that is nothing but reactance value, X value, automatically if you decrease the X value, the maximum capacity will increases. So again you can decrease, automatically the maximum power will be increased. This is you are representing here. And coming to the active and reactive power control. Okay, you can clearly see that figure E. Okay, figure E, we are given voltage. Okay, you can clearly see that we are applying, we are adding, we are injecting voltage with the series with the bus voltage, series with the bus voltage. Automatically what happened, so the angle of driving voltage will be changed, the angle of driving voltage will be changed. And from that we can know that the driving voltage is always perpendicular to the flow of current. So automatically their angle also changes. So once you are changing the angle means, once you are changing the angle means only reactive will be, maximum reactive power will be controlled and minimum effect on the active power. And you see the next figure, we are injecting voltage in driving voltage, same phase with the driving voltage, which does not change the phase angle. It does not change the phase angle. It can increase the magnitude of current. It increase the magnitude of current. Once it increase the magnitude of current means, which can involves the active power change and minimum involvement in the reactive power. That means once angle changes, which is capable to control the reactive power, magnitude increases means which is capable to control the active power. We are need both the active and reactive power control means we can go for this G figure. You can clearly observe that injecting voltage with phasor with series with the lines. Okay, here we are injecting voltage with phasor, some phase angle with the bus voltage. Automatically what happened? The angle changes and magnitude changes. So once means this is also used to control the both active and reactive. So angle changes means which can controls the active, which always gives the reactive power compensation. This is used to control the active power. Both injecting voltage means which can gives the both control on the active power and reactive power. These are the basic types of fact controllers. In general, fact controllers can be divided into four categories. That is series controller, and shunt controller, and combined series controller, and combined series shunt controller. You go in detail with, you can always the fact devices represented. This is the general symbol for the fact controller. So this is series controller. The series controller always connected in series with the transmission line. The series controller always influence on the voltage in the transmission network. So that's why I represented here E. Okay, it is always connected in the series with the transmission line. This is a variable impedance type, that is variable nature of capacitor or variable nature of inductor, which is always influence the voltage in the transmission lines. So that means it can always uh, influence on the reactive power. It is always control the reactive power in the transmission line and minimum involvement in the active power control. So like that you go to the shunt controller. Shunt controller means always the controller is connected in parallel to the transmission network. It is always capable to inject the current in the transmission line. It is capable to inject inductive currents or capacitive currents based on the requirement of the transmission line, and which is also a variable impedance type, whether it is a capacitive nature or inductive nature. And the main advantage of the shunt fact controller, like series controller, it is also controls the reactive power, which is less impact on the active power conversion. And coming to the third one is, this is indicating unified, whether it is a combined model of series controller. If you connect with the DC power link, it is called as unified. Otherwise, if you connect with some AC links, it is called as coordinated. You can clearly see that here we are having two AC lines, individual transmission line reactive power controller. Reactive power can be controlled by these individual controllers, and combinedly you are connecting with the DC power link. It is capable to control the active power. So for example, you have surplus active power generation in this area. Through DC power link, you can send to the second area. So mutual exchange is possible through DC power link for the controlling of active power. As usual, these series controllers can control reactive power in the individual lines. And coming to the uh, this is the example for the coordinated series and shunt controllers. Individually, this series and shunt controllers can control the reactive power by injecting the current here and influence on the voltage here, and it is capable to exchange the active power through this coordinated control. So we can clearly understood from the basic types of controllers. So individual series and shunt controllers are capable to control maximum reactive power. If the requirement is both active and reactive power controller, means you need to prefer the combined series controller or combined series shunt controller. Whether it is connected with DC link, it is called as unified. Otherwise it is called as connected in coordinated manner. And these are the some of the examples for combined controllers. And these are the key benefits from the fact controllers. The major disadvantages of the AC transmission system can be solved here. That is, the uncontrolled power flow can be converted into control of power flow. So control of power flow as ordered, that is the major advantage of the fact controllers. Automatically the active power transfer capability increases, that is increase the loading capability of lines. Automatically system security increases, and greater flexibility in setting new generation, and lines also upgraded, and always which reduces the reactive power flows and allowing the lines to carry more active power, reduce the low flows and increase utilization of low cost generation. These are the some of the key benefits from the fact controllers. So this is the last concept of the first module, that is principal high power device characteristics and requirements. So the material which are used in the designing of these fact controllers, must be capable to carry a high voltage and high current. So that's why we are using regularly a silicon wafers, and the diameter nearly it is 75 to 125 mm, up to pushing towards the 150 mm in diameter. The same diameter device can be made for the high voltage with lower current and vice versa. This can be done used on doping. And potentially silicon crystal have a very high voltage breakdown strength of 200 kilovolts per centimeter and a resistivity somewhere in between the metal and insulator. So automatically doping with impurities is always results, uh, current capability always increases and voltage capabilities decreases. If you require voltage capability is high and lower current capability, always you prefer for lower doping. So based on your doping impurities, we can change the material from high voltage decreases. If you require a current capability is high, automatically you can dope with high impurities. Low doping always gives the uh, low current capability. So these are the general criteria. 125 millimeter device may have current carrying capability of 3000 to 4000 amperes, and the voltage withstand capability in the range of 6000 to 10,000 volts. The highest blocking capacity along with other desired characteristics is somewhat in the range of 8 to 10 kV of thyristors and 5 to 8 kV of GTOs and 3 to 5 kV for IGBTs. That's why you are mostly preferring the thyristors for FAC devices. The second one is losses and speed of switching. Always the forward voltage drop and consequent losses during the full conducting state. This is the on state losses. So always some losses is there during the switches when it is operating, and speed of switching also one of the matter. So these are parameter trade-off devices. So parameter trade-off devices means the switches which are used in the FAC devices always require some power for the gate, and this is also always required the di by dt capability and dv by dt capability. That means you always require some uh, turn on and turn off capability limits, like that, turn on and turn off capability. And you can take the uniformity of characteristics, whether you consider the material silicon, the material entire the characteristics required uniform characteristics, and the material which are used for the designing of this FAC devices always required some quality, and the manufacturing environment always required some clean and neat. These are the some parameter trade-off devices. These are the some key factors in the module 1 we are covered. So what are the disadvantages of HVAC DC systems? So what is the need of interconnections and what is the advantage of FAC devices, and how we are controlling the active power, reactive power, and which parameters the active power and reactive power dependent. All these things in the covered in the first module. Thank you.